Hi everyone. In this video, I am going to explain about Prim's algorithm. This Prim's algorithm is used to construct minimum spanning tree. In my previous video, part 31, I explained about what you mean by minimum spanning tree and how to construct minimum spanning tree for the given graph by taking a simple example. Okay, just for the new viewers. So the minimum spanning tree is the tree for the given graph, which includes all the vertices of the given graph without cycle. This is what the minimum spanning tree. So in order to construct minimum spanning tree for the given graph, we have two algorithms. One is Prim's algorithm and another one is Kruskal algorithm. So in this video, we are going to discuss about how Prim's algorithm is used to construct minimum spanning tree for the given graph. So this is the given graph, okay, which is having 6 vertices, namely A, B, C, D, E, F. For this graph, we need to construct minimum spanning tree using Prim's algorithm. To construct the minimum spanning tree for this given graph, so I am constructing one table which is including 3 columns. One is tree vertices, that means which are the vertices included in the spanning tree. So I'm calling this as an VT. Okay, that means capital V T. Okay, that means which are the vertices included in our tree. These are vertices included in our tree. So remaining what, see, what is the definition of the graph? We know that graph G is equal to set of vertices and edges. That is set of, there is a flower bracket, or a set of vertices and edges. So and we know that, so here vertices in our this example, set of vertices is equal to what and all, or set of vertices is nothing but A, B, C, D, E, F. Vertices or edges, both are set vertices and are also called as nodes. Okay, so this A, these are the nodes, so the which are written within the circle. Okay, nodes, these are the nodes, are also called as vertices. These are the set of vertices. Okay, so now I need to say which are the vertices I currently included in the tree. So currently I am not considered any tree, so empty. Now what we need to do, first select any one vertex arbitrarily. Arbitrarily means randomly you select any one vertex. So which vertex I can select? Let us take, I selected A, and I will return dash comma dash. That means, so the first parameter what it says, so I reached A from which node? That means from which vertex I reached A, and the distance what? First one indicates from which vertex, second one indicates the distance traveled to reach from this vertex to this vertex. Okay, so this is what it says. So now out of this A, B, C, D, E, F, now I have included in my tree what? 1. So that means now this is my partially constructed minimum spanning tree. Right now I am having only one vertex in my partially constructed minimum spanning tree. Okay, so now this is my the first step. What I did in the first step, out of the given set of vertices, randomly I selected any one vertex as a starting vertex, and that is the only I include. That's what VT. That means vertices included in the spanning tree, short form VT. So which is the vertex included in minimum spanning tree? Only one vertex, that is A. Now which are the remaining? So out of this one A, B, C, D, E, now one is included, means which are the remaining? B, C, D, E and F. Now you just tell me B is at a distance from A what? Now B is at a distance 3 from A. So I will write B of A comma 3. Okay, the meaning is B is at a distance A from 3. That means from A, B is at a distance 3. That's the meaning. Similarly, C. Since C is not directly connected to A. See, C is connected to A now? No. Since C is not directly connected to A, I will write dash comma infinity. That means C is not connected, so I cannot reach from A to C. From A I cannot reach, so dash, and since I don't know how to reach C, so I write infinity, some larger value. Similarly D, again D is also not connected directly from A, so again I will write D of dash comma infinity. So E is connected directly from A. Yes, E is connected directly to A, and E is at a distance 6 from A. So what I can write? Yes, A comma 6. So that means E is at a distance 6 from A, or from A, E is at a distance 6, whatever you can call. Okay. So now F is directly connected to A. Yes, F is directly connected to A. That is a distance 5. So I'll write F of A comma 5. That means from A, F is at a distance 5. This is what I did the first step. Okay. Now this is my partially constructed. Now remaining vertices. So how I can get remaining vertices? Now whatever I include in my VT. So right now in my VT, what I included? In my VT, initially null. Now what I included? Now I included A. Okay. So now, which are the remaining vertices? If I minus A, B, C, D, E, F. Minus A means A get cancelled. Remaining is B, C, D, F. So remaining vertices, what I can say? Remaining vertices I can say what? V minus VT. This is what my remaining vertices. Okay. V minus VT is my remaining vertices. Right now, how many vertices we visited? We visited only one, that is vertex A. Remaining vertices A, B, C, D, E, F not visited. That means A is visited, these are unvisited. So I can either three vertices, I also called as these are visited vertices, and these are what? Unvisited vertices. Unvisited vertices. Visited, unvisited. Visited, unvisited. Now, whenever we are moving from one vertex to another vertex, always we need to move from visited to unvisited. Always we move to what? Visited to unvisited. Now here visited is what? A. Now from A, among the unvisited, that means among the remaining vertices, select one edge which is at a short distance. See, look into the diagram, graph. From A, I can see 3, 5, 6. 3, 3, 5, 6, infinity. 3, infinity, infinity, 6, 5. Which is minimum among here? So 3 is minimum. That means from A, if you reach F, you have to travel 5. If you travel from A to E, you need to travel distance of 6. But B you can reach shortly. So that from A, shortest vertex is 3. So you select the edge in such a way that from the visited vertex, it should be shortest. Now which is the visited? A. From this, which is shortest? From A, which is shortest? 3, 5, 6, B. So I am selecting this one. So now in my vertex, in my tree vertex, now I will include B. That means this is my previously constructed, partially constructed minimum spanning tree. To this one, I am including this B. So A and this become B. Now this is my what? Partially constructed minimum spanning tree. Now which vertex I included now? I included what? B also in my tree vertices. So A, B over. Remaining vertices are, see, V minus VT, A cancel, B cancel, C, D, F. So C, D, E, F. So C, D, E, F. Now you write what? C. Now earlier C is infinity. Now from B it is at least directly connected to E. From A is not connected. From B it is connected to C. Yes. B is connected directly to C at a distance 1. So I can write C is at a distance 1 from B. That means from B, C is at a distance 1. Okay, similarly D. See, when I'm writing, you should think one more. So whenever you're writing, the new value and the previous value you need to compare. Whichever it is the minimum, that we need to return. In this case, 1 is minimum when compared to infinity, I return. Suppose this is maximum and the previous value is minimum, so we need to return the minimum only. So whichever the minimum, that I need to return. Now D. Initially dash comma infinity. Now check. Now right now we are in B. Right now we are in B. From B, D is directly connected. No. From B, D is not directly connected. So again it is dash comma infinity. Now also dash comma infinity. Previously also dash comma infinity. Now any one I can return. Now check E. From B it is what? Dash comma infinity. From B it is dash comma infinity. Which one? E. I'm writing for E now. I'm writing for E. From B it is E is not directly connected, so dash comma infinity. But previously it is A comma 6. 6 and infinity, which is minimum is 6. So I'm retaining the previous only. Now F. From B, F is directly connected. Yes, you see now, B is directly connected to F and distance is 4. But previous value is 5. 4 or 5, which is minimum 4. So I am writing the new value, that is BE. F is at a distance 4 from B. B is at a distance 4 from B. So this is a new value which is lesser than the previous one. So a new updated the new value. Now this is my remaining vertices. Now among this, again you selected the minimum one. 1, infinity, 6, 4, which is minimum. 1 is minimum. So I am selecting this one. Okay. Now to this partially constructed spanning tree, now I am including one more vertex edge, that is C. C I am reaching from where? From B. See, this is 1, this is 3. So okay, this is my partially constructed spanning tree right now, as of now. Now remaining vertices are what? See, now A, B, C I included. So now I am including what? C also included in my VT. Now remaining are what? D, E, F. So D, E, F. Now D. Now check. Previously it was dash comma infinity. So now we are at what? We are at C node. We are at this C node. So now you check. From C, D is directly connected. Yes. D is connected directly to C at a distance 6. So now this is what D is from C, it is a distance 6 and previously it was infinity. This value is minimum, so I am taking the new value. Now E, now right now I am C. E is at a distance, C is directly connected to E, no, it is infinity, but previous value is 6, so it is minimum, so I am retaining the new value. F, see from C, F is a distance 4. From C, F is a distance. Previously also F is 4. Now both, now previous value also 4. From B, from C also 4. That means, see, whether you are reaching F from B also 4, C also 4. Both are same. But see, whether you are reach from here also 4, from here also 4. No difference. Either you retain the previous or you write the new one. So I am retaining the previous only. Okay, you can retain, you can update the new value also, C comma 4 also. That is also right for this problem. Now this is my current. So these are the tree vertices included in my spanning tree. These are the remaining vertices. Now among 6, 6, 4, which is minimum, 4 is minimum. So I am selecting this vertex. Since now I selected F, now this is my previously constructed what? Spanning tree. Now I reach what? F. From where? I reach F. From where? From B. So this is my F. This is this one. So this is distance 4. This is my partially constructed spanning tree. Now among these three, F also included. So F also included in my what? VT. Now remaining what is what? Only D and F. D and E. Sorry, D and D. So now I'm writing D. Now you check. D from F is a distance what? D is a distance 5 from F, but previously it was 6. See, previously D is a distance 6 from C, but D is a distance 5 from F. So 6 or 5, which is minimum 5. So I'm retaining right the 5 previous one, new one 5. So next E. E is at a distance. See, E is a distance from A it is 6, but from F it is 2. From A 6, from F is 2, which is minimum 2. So I'm updating. So E is at a distance from F, it is 2. Okay. Now among these two, which is minimum, among these two, this is minimum. So I am selecting this E vertex. So now remaining is what? Only this one. I will update later. So now this is my what? Previously constructed what? Spanning tree. Partial spanning tree. Now to this I am adding what? E. So E is from where? E I am reaching from F. So from F at a distance 2. This is my partially constructed spanning tree. Now remaining is what? Remaining only is 1 D. So now check. from E. Now, right now we are in E. Check the graph. From E, D is a distance 8. D is a distance 8 from E. But from previous value, what says? Previous value is 5. 5 or 8, which is minimum 5 only. So, I am retaining the previous value only. See, there is only one, no option for selecting. This only I need to select. Okay. So, I selected this one. So, that is D of F comma 5. So, nothing will be remaining. So, now this is what my previously constructed what? Spanning tree. Now, to this I am adding what? D. So, I am reaching from what? F. So, I am writing here D and I am reaching from here. Now, see, I included D also now. So, F, E, D also. So, all are now. You minus this one, V minus VT. A get cancelled, B get cancelled, C, D, E cancelled, F cancelled, D cancelled. Okay, now it is empty. Remaining vertices are empty. That means what? We have included all the vertices. You see, we include how many vertices are there? A, B, C, D, E, F, 6 vertices. So, all the vertices we have included. And any cycle is there? No cycle. So, this is our minimum spanning tree. Okay, this is how our Prim's algorithm construct the minimum spanning tree for the given graph. Now let us write the algorithm, Prim's algorithm to construct this minimum spanning tree for the given graph. Okay, so now what is the first step we did? Among the given vertices, we have selected any one vertex, correct? So that vertex, which one we selected? A. But always we select A? No. Somebody will select B, somebody will select E, somebody will select C, somebody will select F, somebody will select D, whatever. That means we can select any vertex, right? Okay. So which one? VT. Which one is selected? A, we selected. So initially what I will say, so VT, that means which vertex I selected. So generally what I will say, small v, not. That means this is my initial vertex. I selected one vertex. This is my initial vertex V0. In general, whatever it may be. Now, once I selected this vertex A, is there any edges form? Because no only one vertex, there is no edge. That means which are the edges are there in my current partial spanning tree? No. So I will take now one more variable called ET. It indicates which are the edges included in the tree. Okay, repeat. ET indicates the set. Okay, ET indicates the set. Okay, it will says which are the edges we included right now in our spanning tree. Right now in the first step, which are the edges? Null. So I will say it is a null. Okay. So now what I have to do? Next step, what we did? We selected one among the remaining vertices. Then again we selected one. We selected one more. We selected. That means we repeated this operation. What we repeated? Selecting the nearest vertex. That means for repeating, what we have to use? For repeating, we need to use what? Loops. Which one loop? Here I will use for loop. Why? Because I know how many number of times I have to select. See here, if you take how many vertices are there? How many vertices are there? 1, 2, 3, 4, 5, 6. How many edges are in the minimum spanning tree? 1, 2, 3, 4, 5. If there are 6 vertices are there, we need what? 5 vertices. Let us take one more simple example. Assume this is the graph which has 4 vertices, and for this is the minimum spanning tree. How many edges are there here? 1, 2, 3, 4 vertices. That means for 4 vertices there are 3 edges. For 5 vertices, 4 edges. For 6 vertices in this example, 6 vertices, we got what? 5 edges. 1, 2, 3, 4, 5. So 5. So in general, if there are n number of vertices, n minus 1. So how many number of vertices are there? That minus 1. So we'll say V says a set of vertices, whereas modulus of V says number of vertices. Okay, modulus of V says number of vertices. So we'll write now how many vertices say? Number of vertices minus 1. So we'll say for I is equal to from 1 to number of vertices minus 1. These many times I need to do the selection operation. Okay, so now what we did in the first step, after selecting one vertex randomly, we selected the minimum edge, that is 3, 5, 6 infinity, minimum edge. Okay, among what? Among the remaining vertices, such that what? One should be visited, another should be unvisited. Okay, one should be visited, another should be unvisited. Okay, so that we integrate. Okay, for each one, what you have to do? Now we need to do what? Inside the loop, find the minimum weighted edge See, this is what we did. We find the minimum 3 infinity infinity 6 5 minimum weighted edge we find out. Okay, find edge. So that edge I will say star E star is equal to what? V star comma U star. So I told already. Okay, so what is that? Whenever we are moving, we need to move from what? Visited to unvisited. So this is V and this is my U. Always we need to, that means always you need to move that V star visited to unvisited. Okay, unvisited such a way that what? V star should be in what? It should be visited or what? V star. V should be in visited. That means VT should be in VT. See, this is what visited. This is what visited. VT. And U star should be in where? U star should be what? In unvisited. This is unvisited. Okay. U star should be in unvisited. That will remain. That means V minus VT. Okay, so now I selected that one edge, and that one edge where I included in the tree vertices. That's why this is the previously selected tree vertex. To this I am including. So that means I need to include in VT. That means VT union that U star, unvisited vertex U star. That means I am including this vertex in VT. This is my updated VT. Whenever I include one more vertex, so it makes one edge, right? So that edge also I need to include my ET. Okay, I told ET. Okay, so ET earlier was initially null. Now one edge, which is that one edge A to B. So A, B edge I included. So ET is equal to what? ET union which edge? E star. This is what the edge we selected. Okay, so this is the algorithm for the prims. Okay, and for finally we need to return what? ET. This is our solution vector. Okay, now we'll trace. Now up to here is over, right? Now I find out this one, this is done. Now the remaining vertex is this one. Now what? B is V star visited, these are unvisited. Now again, I becomes 2, 2 is less than or equal to 5, true, comes inside. Now again find the minimum weighted edge. Among the minimum edges of 1 infinity 6 4, 1 is the minimum. So I selected this edge. This edge is what? From B to C. B should be what? That means from edge B to C. B to C means what? This should be visited, unvisited. See, B is visited, C is unvisited. So B comma C, that B, C I am including here. C I am including in my partial tree included. So that BC I include my ET. Next time I becomes 3, 3 less than or equal to 6 minus 1, true, come inside. So again I am finding minimum 1. Among this is minimum. See, right now B is what? He visited. F is what? Unvisited. So F I am including. So F I am including in C, I including in F. Okay, so if I including, that is B to F, this edge I am including. Next I becomes 4, 4 less than or equal to 5, true. So comes inside. So again among these two it will select any one, that is E. That means from F to E. F to E means F I am including E. Okay, F all visited, E. F to E included. So that is F to E. So next 5 less than or equal to 5, true. Only one is there. I selected, that is F2D. F2D I included. So these are the edges what we are having in my span tree. See here. So A to B, B to C, F to D, F to E, B to F. These are the edges which forms the minimum spanning tree. Okay. So this was the Prim's algorithm. This is how Prim's algorithm constructed the minimum spanning tree. This is our algorithm. Hope you understood this algorithm. Okay. Now let us do for this one analysis. See, what is the definition of a minimum spanning tree? Minimum spanning tree is the tree for this given graph which includes all the vertices included without cycle. So initially, that means whether we are including all the vertices at the same time, no. I am selecting one by one. This Prim's algorithm uses greedy technique. Greedy technique says it works stage by stage by selecting only one input at a time. So first time select one vertex, next one more vertex, next one more vertex, next one more vertex, next one more, like that. 1, 2, 3, 4, 5, 6. So like that, every time the problem size is increasing. First time, how many vertices I need to include? All 6. 1 include, remaining is what? 5. Next time included the second vertex. So 2 vertices included. Remaining is what? 4. Next time included one more. 3 vertices. Remaining was 3. Next time one more insert. Remaining was 2. See, from 6 to 5, 5 to 4, 4 to 3, 3 to 2, 2 to 1. The number of vertices to be included keep reducing. So which basic efficiency class it keeps reducing the problem size? Log n. Okay, log n. There the number, but here it is number of vertices. Number of vertices which want to be taken? Modulus of v. So I'll say mod log of mod v. Each time I need to check all the edges. Maximum, all the edges I need to check which is minimum. So E number of edges. So we'll say modulus of E. So the time complexity of our Prim's algorithm is mod E log mod V. That means E times we need to text log V. So this is the time complexity of our Prim's algorithm. Hope you people understood the concept of Prim's algorithm and how to construct the minimum spanning tree by using what? Prim's algorithm. Thank you. Thanks for watching. If you have any questions, please write it in the comments. Thank you. Thanks for watching.